So in the previous video, we have talked about this necessary condition for differentiable function, which tells you that if f is differentiable, that implies the CR equations are satisfied. What is CR equation? If f is of the form u plus iv, then ux, that is a partial derivative of u with respect to x, is same as vy, and uy will be same as minus vx. Now here we are discussing about the sufficient condition for differentiability. We also talked that converse of this result is not true. That means a CR equations are satisfied, we cannot say a function is differentiable. So the question is, what extra condition you apply on this side so that the function will become differentiable? So that is known as a sufficient condition for differentiability. So in this video we are talking about what are the extra condition is required to function become a differentiable. The CR equation is satisfied plus something more is required to make a function as a differentiable function. So before that, I want to recall one of the concept from the advanced calculus 1, that is functions of several variable, the definition of a differentiable function. Let us consider a function phi of two variable which is defined over the domain D, and this domain is contain some neighborhood of x0 y0 where x0 y0 also belongs to D. If I want to say this phi function is differentiable, then it has to be satisfied that phi of x plus h y plus k is equal to phi of xy plus h into phi x at xy k into phi y at xy plus h into epsilon 1 hk plus k into epsilon 2 hk. They are the error terms where this epsilon 1 hk and epsilon 2 hk will tends to 0 as hk tends to 0, 0. So this is the definition of function is differentiable, or phi is differentiable if this is satisfied. So for functions of two variable, this concept is If you want to know about this concept more, you may see my videos on differentiable function for two variables. I will write down the link for this video also in the description. Please check that. Now let us study the objective of the video is the sufficient condition for differentiability. Let us talk about that. So let a function f of z, which is u of xy plus iv of xy, be defined throughout some epsilon neighborhood of point z0 equal to x0 plus iy0, and suppose that the first order partial derivative, that is ux, uy, vx, vy, exist everywhere inside the neighborhood of x0 y0, and they are continuous at point x0 y0. The first order partial derivatives are exist and they are continuous at this point z0. The second one, and they satisfy the Cauchy-Riemann equation, that is CR equation, that is ux is equal to vy and uy equal to minus vx at the point x is 0 y0. Then prove that f dash of z0 is exist and its value is f dash of z0 is ux at x0 y0 plus I Vx at x0 y0. So this is the statement of sufficient condition for differentiability, which tells you that the first order partial derivatives are exist and they are continuous, and if they satisfy the CR equations, then the function is differentiable function. That means its derivatives exist. So let us try to prove the statement. So we'll assume that this condition or the statement A and B are true. Suppose that this is true. What is A statement? It says that the first order partial derivatives exist and they are continuous. The second statement is says that CR equations are satisfied. Let us write delta z as delta x plus I delta y, and we are taking this delta z as very small quantity in the neighborhood of epsilon neighborhood of delta z that we are taking. Delta w I may write as f of z plus delta z minus f of z. Since this is the point z0, I am taking as f of z0 plus delta z f of z0, where I may write delta u of x0 plus delta x, y0 plus delta y minus u of x0 y0. Delta v I may write as v of x0 plus delta x, y0 plus delta y minus v of x0 y0. Now we have assumed that the first order partial derivatives are continuous, and if you can recall the statement of advanced calculus, it says that the first order partial derivatives are continuous, then a function will become differentiable. So that means we can say that u and v are differentiable functions at point x0 y0, because that theorem says that fx, if f is a function of two variable, it says that if fx is exist and fy is continuous, then f is differentiable. So due to this result, we can say that u and v are differentiable function. And so if they are the differentiable function, according to the definition, that we can write as u of x0 plus delta x. Now you just recall the definition which we have stated in the starting of this video, that is phi of x plus h and k. So instead of h and k, I am writing delta x and delta y, because they are the increment in x and y. So that's why I can write this as u of x0 plus delta x, y0 plus delta y equal to u of x0 y0 plus ux at x0 y0 into delta x plus delta y into uy x0 y0 plus delta x into epsilon 1 delta x delta y plus delta y into epsilon 2 delta x delta y. Now this equation, due to this delta u equal to this, we may rewrite as delta u equal to u x x0 y0 into delta x, uy at x0 y0 into delta y plus epsilon 1 delta x delta y delta into delta x, epsilon 2 delta x delta y into delta y, where this epsilon 1 and epsilon 2 tends to 0 as delta x delta y tends to 0 0. Similarly, for v is also differentiable, so for that I may write as delta v equal to vx at x0 y0 into delta x, vy at x0 y0 into delta y, plus here we have another function, not same epsilon 1 epsilon 2, so I may write this as epsilon 3 delta x delta y delta x, epsilon 4 delta x delta y into delta y, and here is also epsilon 3 epsilon 4 tends to 0 as delta x delta y tends to 0. They are the error functions, so that's why they are tending to 0. So what will be the delta w if you substitute this both value into the delta w? So delta w is delta u plus I delta v. So what will be this? So this will be ux. Now instead of writing ux x0 y0, I just write down ux, and you may understand that ux means it is at the point, I'm talking about at the point x0 y0. Okay, so it is ux delta x plus uy delta y plus epsilon 1 delta x, epsilon 1 delta x delta y into delta x plus epsilon 2 delta x delta y into delta y plus I Vx delta x plus Vy delta y plus epsilon 3 delta x delta y into delta x plus epsilon 4 delta x delta y into delta y. Now also by the hypothesis it says that the CR equations are satisfied. So since CR equations are satisfied, you know that it is Ux is equal to Vy and Uy equal to minus Vx. So if you use that one here in these two places, what we get instead of Vx we get Uy. So here this value is minus Uy and this value you will have is Ux. So what you will get by simplifying this, Ui is common out from this two quantity now and Ux is common out from this two quantity. So what you will get, delta W will be written as Ux delta x plus I delta y, because this I is multiplied to here and Ux is common from this quantity and this quantity, plus Uy into from this two quantity. Uy is common out and this, so I am writing this two quantity as it is for now and let's see what is happening. So that is delta y minus I delta x plus what are the other quantities we'll have. The other quantities are this quantities. So here is also we have I is multiplied to here. So that's why we have epsilon 1 delta x delta y plus I epsilon 3 delta x delta y into delta x. The last quantity we'll have delta 2 delta x delta y plus I delta 4 delta x delta y into delta y. So delta y is also common from that too. Let us concentrate on this quantity. So what we have is this delta y minus I delta x. So if I write down this is as minus I square delta y minus I delta x. So what we have written is just here I have multiply and divide by minus 1 and minus y I have written as I square. So it is minus 1 I square, and if I common out now I from this minus I from this, then what we'll have is delta x plus I delta y. So we'll have instead of this now just say that it is delta x plus I delta y. Instead of this place we can substitute, and this delta x plus I delta y is already there, and delta x plus I delta y we can write as delta z, and that I can take common out and I may write down as in the denominator of that. So I'm dividing by delta z both the side. So you will have Ux here and this minus I is multiply here, so it is minus I Uy plus epsilon 1 delta x delta y plus I epsilon 3 delta x delta y into delta x upon delta z plus epsilon 2 delta x delta y plus I epsilon 4 delta x delta y into delta y upon delta z. Now let us concentrate on this quantity delta x upon delta z delta y upon delta z. See this quantity epsilon 1, epsilon 3, epsilon 2, epsilon 4 are tending to 0 if I take the limit delta x delta y tends to 0. So if I prove that these quantities which are here they are bounded quantities, then we are through. So what is, you will have delta x is always less than or equal to mode of delta x is always less than or equal to mode of delta x plus I delta y, due to the real part of z is always less than or equal to mode z. Due to this we can have this, and this is what there is delta mode z. So we'll have here is delta x upon delta z mode delta z is less than or equal to 1. Similarly delta y upon delta z will be less than or equal to 1. Mode of delta y upon mode of delta z is less than or equal to 1. So let us concentrate on these two quantities, but what we can say is epsilon 1 delta x delta y plus I epsilon 3 delta x delta y into this quantity is less than or equal to epsilon 1 plus epsilon 2, and this epsilon 1 and epsilon 2 will tends to 0 as delta x delta y tends to 0. Similarly, epsilon 3 delta x delta y plus I epsilon 2 delta x delta y plus I epsilon 4 delta x delta y into delta y upon delta z mode of that is less than or equal to epsilon 2 plus epsilon 4, here it will have 3, and this will tends to 0 as delta x delta y tends to. That means in this equation star, if I take the limit both the side by limit delta z tends to 0, this quantity will tends to 0 and this quantity will tends to 0. So that's why you will have a limit of delta z tends to 0, delta w upon delta z is ux minus I uy, and you know that this limit is exist because ux and uy are exist, which is the hypothesis. So that's why this is nothing but the derivative of the function at the point z0, that is ux minus iui. According to the CR equation, ui is nothing but the minus vx. So if you use that, this is ux plus ivx. So that completes the proof of sufficient condition for differentiability, which tells you that if the partial derivatives exist and they are continuous at the point and the CR equations are satisfied, then the function has to be differentiable. So whenever you want to prove that the function is differentiable, then you have to check the two conditions. The first one, all the partial derivatives should be exist and they are continuous, and the second one, the CR equations are satisfied. So let us try to solve some examples with the help of that, so that f of z is equal to e power z is differentiable everywhere. So what is this f of z? It is e power z, which we can write in the using the Euler's formula, e raised to x cos y plus I sin y. So what is your real part here? U of xy is e power x cos y, v of xy is e power x sin y. So what you will have, ux is e raised to x cos y, because the derivative of this with respect to x is e raised to x cos y. Uy is e raised to x sin y minus vx you will have is e raised to x sin y, and vy is e raised to x cos y. So you said, notice that this ux, ui, vx, vy are continuous everywhere due to exponential function and the trigonometric functions are there, and you know that the product of two continuous function is continuous in functions of two variable. So that's why this ux and ui are continuous, vx and vy are continuous, and you just notice that ux is equal to vy and ui equal to minus vx. So that means CR equations are also satisfying. So the partial derivatives are continuous and the CR equations are satisfying. So we can say that the function is differentiable. So therefore f is differentiable everywhere. And what will be the derivative of that function? That is f dash of z, that is ux plus ivx as per the formula we have derived, that is e raised to x cos y, that is ux is we have here, vx is e raised to x sin y plus I e raised to x sin y. So that we can write e raised to x is common out, cos y plus I sin y, and that can be written as e raised to x into e raised to iy, which is same as e raised to I sin. So what we have proved here is derivative of e raised to z is e raised to z. Second one that I am giving you as a homework, that is prove that f of z is equal to z raised to 3 is differentiable everywhere. This is the first example that I am giving you as a homework. And the second example you may try for this, that is 1 upon z raised to 3 is differentiable everywhere where z is not equal to 0 in the domain. So try for this two example. Third one that I am giving you as a homework, but with that homework I'm also explaining you one more thing here. So if you have f of z, which is under root of mod of xy, so that CR equations are satisfied at 0 0, but the function is not differentiable. See, one of the example of such type we have discussed in my previous video also, that is z bar square upon z. This is the example we have discussed, where the CR equations are satisfied but the function is not differentiable, which is the converse of sufficient condition. So this is also a same kind of example is there. So try for this three example. So let us recall what we did in this video. We have discussed actually a necessary condition for differentiability, which tells you that if the function u plus iv, whose real part and imaginary parts, the partial derivatives of first order are exist and they are continuous, and if they are satisfying the CR equation, then the function must be differentiable. We have seen that the converse of that result is also hold by a sufficient condition. That means the function is differentiable, then we can say that it's satisfying CR equation. So actually that result we can state it as if and only if f is differentiable if and only first order partial derivatives exist, they are continuous and CR equations are satisfied. So we can state that is as a combine both the result, that is necessary and sufficient condition. So that's it for this video. If you like this video, please press the like button. If you have any comment, suggestion and a question, please drop down in a comment box below. Till then, bye bye. See you in next video.